All right, I want to take a minute to hit some of the high points in Chapter 3 on probability. And just want to start with this example in the beginning of Chapter 3, where it talks about using this thing called the fundamental counting principle. What is that? Well, it says that if there are, let's say, m ways to do one thing, and there are n ways to do another thing, then, so write this out a little bit better, then there are m times n ways to do both. Okay, so let's take a look at this example here. You have three cars types, manufacturers that you could possibly do. You have two sizes that you could pick from either one of those, and then 1, 2, 3, 4 colors that you could pick in that regard. So the question that we're trying to ask here is how many different ways can you select all of that stuff and to get an answer? Well, you can follow this rule for any number of ways. You can have 2 ways or 200 ways. And this tree diagram is a nice way to prove that, if you will, so that you understand the concept, which will make it easier to apply the rule. Notice if we just go with the Ford off the top, you have 2 choices with the Ford. You can get a compact or a midsize, and in each case you can get the same 4 color options. Well, the same is true for GM and for Honda. And so if there are 8 ways that you see down here, all 3 manufacturer choices have 8 ways to do it. 3 times 8, I think everybody knows, is 24. So that's a basic example, and in the chapter content you'll see a lot of tree diagrams as ways to understand various probability concepts, and that's because it's easy to see. Now for certain problems there's too many permutations, so you wouldn't use a tree diagram, you would rely on the formula itself. Now, conditional probability. This is an entirely different thing, and I want to try to give you a picture version of it so that we can understand what's going on here. First, though, I do want to get out of the way some of these jargons here. So this symbol here, a P, and then in parentheses B, vertical bar A. It is translated here. It's the probability of B given A. So whatever A is, it's an event, and so is B. If there is no event A, then there is no event B. So this means that these things are conditional. One is conditional on the other. So let's use a Venn diagram. Let's say that event A, the conditional one, the one that has to happen for B to happen, it will just symbolize it as that circle. And then event B is intersecting A in some way. And so one way to think about a conditional probability is in terms of what these 2 regions have in common. And so in a Venn diagram, we call this an intersection because these 2 regions and whatever they represent have intersected. And we like to symbolize that as A intersect B. And that upside down U actually usually is supposed to be a little bit wider. I'm going to change colors. Okay, and it means intersection. Okay, just a math symbol. And so there's some jargon technicalities to get over when you're just reading this stuff and the way that we represent it. So let's think a little bit more deeply about a probability. And so given that you've already read and you know that the probability of any event is just defined to be uh, successes over possibilities. And know that by possibilities, we mean uh, successes plus failures. Okay? So we could call it success over success plus failure, just to give a shorthand there. And so that is always the way you calculate a probability. And what gets interesting is the number of ways to count successes and failures. We have some advanced and simple ways to do that, and it just depends on the nature of your problem. And so we'll get to the various ways of counting other than the fundamental counting principle later. But for now, let's get back to this conditional probability. But I did want to highlight what is probability just as a reminder. So the probability of B given A. Well, in our case, the successes, okay, those only happen in the intersection region. They can't happen anywhere else. Only where A and B intersect. Because B only exists given A. And so we could write the probability of B given A as, well, the probability of that intersection, since we just determined that logically, and the possibilities. Well, what do we mean by the possibilities? Well, the possibilities are only in A. This is the region where all of that is possible. And even in the intersection region there. And so we would simply write the probability of A. And so in a conditional probability, and this will help you, a lot of your conditional probabilities will come out in a tabular format, and I'll be addressing that in a voice thread of the chapter content. But if you have a conditional probability, just know that the condition, which is always the thing following the bar, that is the sum of your possibilities. And so if you can identify that, and it'll be interesting, this intersection idea, you'll have an intersection in a table, row and column intersection. And so we'll try to combine those ideas in a later video. Now, I bring this up because if you pay close attention to what's going on here, this formula has all of the features of that formula. We have the given probability. We have the conditional part. And we have an intersection. And I didn't keep my colors consistent from the first diagram, but you can see the connection just symbolically that exists here. And so interesting that the way that they give this multiplication rule for the probability of A and B, which is what we mean by an intersection. All right. And it goes on to say here, if these events are independent, then the rule can just be written this way. And so this is important in some of the probability calculations that we'll be doing. If you have a series of independent events that happen in a row, what's the probability of them happening all together? And so this is really just an advanced form of the fundamental counting principle, but in quotient form. And so if I say, the probability of the probability of A and B equals P of A times P of B, well, that's really going to work out to the probability of A is going to be all of the successful A outcomes, and then out of all possibilities. Getting it all scrunched there. And it would be the same thing for B, etc. And all of these things right here, it's not plus, it's going to be times. And so really, this is a number of ways to do something, to do A. This is a number of ways to do B, and etc. We could go on for as many events that we want to run together in a row. And so the way the book pitches it, there's nothing wrong with it, but it is compact, and they don't give you a picture version, at least for the conditional probability. They do for the addition rule. And so if you wanted to follow that on page 158, you could go there. And so let's take a moment and try to get our minds around this business right here. We just did an AND probability. That's where things are together. But what about A or B? Okay. So the trick here is, what if A and B have an intersection? And so I think it's at least partially straightforward that the probability of this or that, we mean take the probability of one thing and the probability of the other thing, one or the other, and what's sum it up. Okay. Problem is if they have an intersection, then you have to subtract out the double counting. You will be double counting in that case. All right. So be careful of that. And here's an example right out of your book, and it's a good example. So I want to focus in on number 2, rolling a die. Okay, and how could we see that graphically? All right, and so we'll be down here looking at this and this answer that's given in this regard. So let's get a different color highlighter out here. And so we need to figure out how these things line up. So we want the probability of rolling a number less than 3 or an odd number. So what would the sample space look like rolling a number less than 3? Well, it looks like this over here. And there's only 2 numbers out of the 6 total that satisfy that condition. All right. Let's see here. Get this pink one going. What about or an odd number? Okay, well, the odd numbers are 1, 3, and 5. And there are 3 of those. Only 3 numbers, odd numbers, on a regular dice. Well, it becomes quite clear in looking at this that there is an intersection right here. There is a number in the middle that appears in both of these counts. So we have to subtract it. Otherwise, we end up double counting it. And you would get 5, 6 instead of 4, 6, which is noticeably different outcome, probabilistically speaking. So if you can draw a picture, the Venn diagram is a nice way to see what's going on in that. So that'll be the end of this lecture, and I look forward to taking a jab at some other stuff here in terms of more advanced counting concepts.